Okay, waiting for people to grab their notes and get ready here. I don't know how many people noticed. I don't know how many people have been in this classroom before, but there's a charging station up here. There's some iPhone cords and USB-C cords and stuff like that. So if your phone's running out of juice, you can just put it there. Yesterday we were talking about this equilibrium system. The equilibrium system that's shown here is the same equilibrium system that we drew or that we wrote out on the previous slide. So in this reaction we've got hydrogen gas reacting with iodine gas. And remember that iodine gas is a really nice, beautiful purple color. It's turning into hydrogen iodide, which is completely colorless. So we start off with a very purple beaker or flask or something like that, and it slowly becomes colorless. But does it ever completely become colorless? Do we ever completely lose the color? No, and that's because this is an equilibrium reaction. We have two competing opposite reactions. As soon as some of the hydrogen in the iodine turns into hydrogen iodide, well, now two of those hydrogen iodide molecules can react together and they can turn back into hydrogen and iodine. So you're never going to completely get one or the other. You're always going to get a mixture of the two. So we're taking a look at three trials. And in the first trial, we started with just reactants. Now, did we ever get completely just products out of this? No. Remember, that's because, yeah, this reaction can go backwards. Okay, well, let's start off with a mixture of both, and let's see what happens. Well, it still reacts, it still goes forward a little bit, but it doesn't completely go forward. Okay, that's interesting. Let's start out with just products. Let's start out with no reactants at all. And here's when we see evidence of a reverse reaction. And that is very typical. That's exactly what you need from an equilibrium system. We did a little bit of math to finish off yesterday. And it was us using stoichiometry to calculate the theoretical yield, or the amount that we would expect to get if there was a 100% reaction. So if we had a concentration of 5 millimoles per liter, keep in mind all of these chemicals are in the same flask. So they're occupying the exact same volume as each other. So it's almost like that liters doesn't exist. We can keep it there, but the liters here means the same thing for liters there. Okay? It's in the same flask and they're in the same container. So if 5 of these reacts to make 10 of these, we would expect to see 10 moles per liter or millimoles per liter to finish off. We don't. In system 1, we expect to see 10 millimoles per liter. How much do we actually get? Look at system 1 and tell me what is the final concentration, the equilibrium concentration of our products. Sky, what's our equilibrium concentration of our products?
7.8.
7.8 millimoles per liter. Would it be pretty easy for you to figure out what kind of a percent yield? We're expecting 10, but we actually got 7.8. What percent is that? Ooh, okay. That's all right. So we're going to do our percent yield calculation. Percent yield is the actual yield that we got. So we actually got 7.8 millimoles per liter. We were expecting to get what value? 10 millimoles per liter. So if you do this calculation, this divided by 10 times 100, well, it's basically like this times 10. What's 7.8 times 10? 78, right? So this should be 78%. 78% reaction. A 78% reaction. If I said you've got a certain reaction and 78% of it turned into products, in your mind, do you think 78%, does that mean you made, like at equilibrium, do you have more products or do you have more reactants? If 78% of your reactants ended up turning into products, do you have more products or do you have more reactants? Let's go back here, because this is 78%, right? So what do we have more of? Do we have more products or do we have more reactants? We have more products. So 78% seems like this equilibrium is products favored. It favors the products under these conditions, okay? Now, take a look. Does this equilibrium, remember the only thing we did was we changed the initial concentrations of all of these things, right? Look through all three of these trials. Does it seem like the products are favored in all three trials? It sure does. Would you agree? 7.8 versus, even if we added these together, right? Like for a total concentration, that's not how you do it, but you know what I mean? For a total concentration of 2.2, 7.8 was way bigger, right? 2.1 versus 0.6, 2.5 versus 0.7. Yeah, so this is way bigger compared to our reactants. And that's very typical. We're going to go kind of summarize some information right now. That's very typical of a products favored at equilibrium reaction. If things are products favored, that means typically it's greater than 50%. Does that make sense? If more than half of your reactants turn into products, then you'll probably have more products than reactants. Does that kind of make sense, that logic? That's a tough thing to wrap your head around. That's like a logical problem. There's, in general, 4 different cases for reactions, okay? Either you can have no reaction. If I put this thing and this thing together and they don't react, what kind of a percent reaction is that? That's a 0% reaction. And so we don't use any sort of arrow to represent that. We say, it's just no reaction. It's just nothing, right? At reactants favored at equilibrium, what do you think? If you set up a system and you end up with more of the stuff that you started with than what you ended up with, if that makes sense, right? You end up with more reactants than products. What percentage actually reacted? Less than 50%, right? Do we know our greater than and less than signs? Most of us? Okay, all right. So if you want to write down the words less than 50%, then go right ahead. That's totally fine. But less than 50%. So what we're going to do is we're going to use an equilibrium arrow, and we're going to use the number less than 50% above it. Now I'm writing small, and that's because I was dumb and I didn't make this bigger than I should have, but because we're talking about equilibrium, we have to use equilibrium arrows. We have to represent that the reaction can go forwards and reverse, okay? So we're just saying less than 50% means that the reactants are favored over the products. Same thing here, we'll still use this as an equilibrium, but if products are favored, we'll say that it's greater than 50%. Does anybody know what the term quantitative reaction means? You get a complete reaction. What does that mean to you, a complete reaction? 100%. Jaden? Everything reacts, right? We're not going to use 100%, because some people have a philosophical problem, you know what I mean? If you have 30 trillion molecules, and only 29,999,999,999,999 of them react. So one doesn't react. Can you say 100% of them reacted?
No.
Ugh. So we're going to say greater than 99%. That's what we kind of define a quantitative reaction as. And if it's a quantitative reaction, we won't use equilibrium arrows. What are we going to use? Just a straight arrow. That's how we would denote to you that something is quantitative. We don't have to put any numbers. If the arrow is only going in one way, then that means most of this is turning into most of that. Hopefully that makes sense. Now, one of our problems, and we're not going to solve this problem right now, but percent reactions don't hold up, okay? They hold up in, you don't have to go back, but I'm going to go back. They hold up in all three of these situations. Here, that's 78%. Here, that's 78%. And here, that's 78%. But if I would have added an unequal amount of these, then it would not have been 78%. Percent reactions, they don't hold up over kind of all sorts of reaction conditions. So I can't say for certain that this thing is going to react 78% of the time, all the time. That's not something that I can say. I can't say that. So it's good to think about percent reactions, but we're going to have to come up with a different system a little bit later on. So percent reaction is not commonly used to describe a chemical equilibrium system because the percent value only applies to a specific temperature, and it only applies to very specific concentrations, okay? The equilibrium constant K, or Kc as we often say, is more commonly used, and we will talk about Kc hopefully at the end of class, maybe tomorrow. So let's take a look at a graph and let's think about what's going on in this equilibrium system. Would you agree this is kind of the same style of graph as we saw yesterday when we were doing the Lego? Would you agree? We had really sharp changes at the beginning and then things flattened out. There's some things that I want you to pay attention to. Let's think about initial, and then we'll think about at equilibrium. Initially, what do we have in our flask? If you think about at the beginning of this reaction, what do we have in our flask? Do we have any HI in our flask? No, at the beginning we have 0, right? We have no HI at all. What do we have? We've got a little bit of hydrogen and we got a little bit of iodine gas. But we do have H2 and I2 gas. Then, at equilibrium, what do we have? Now that's a loaded question. Is it obvious to you when equilibrium is established? For some of us it is, but for some of us it isn't. At what point in time, right? I'm going to draw a dotted line, and then I'm going to draw a line, and then I'm going to move the line across very slowly, and you tell me when to stop because you think we've reached equilibrium at that point in time. So I'm going to just draw a line, and I'm just going to drag it across, okay, from beginning to end. So I'm going to go slowly, and you yell at me, and you yell at me when you want to stop. I think somebody's selling coffee and cookies, maybe. Or maybe they're coming to grab my recycling. Hi! Does anybody want any coffee or hot chocolate? No, I don't have it. Oh, I inherited it from the teacher who retired. Oh, that's cool. Yeah. Sorry. Yeah, I don't have any money. Thank you. That's okay. Take care. See ya. Okay, I'm going to drag this line across, and you're going to yell at me and tell me when to stop, because that's when we've reached equilibrium.
Now.
Can we kind of agree that, I mean, yeah, but right there, probably. Yep. That's me being a jerk, so I apologize, okay? But yeah, that's when we've established equilibrium. How do you know we've established equilibrium at that point? Yeah, is the concentration of hydrogen iodide changing at that point on? No. Do you know, is hydrogen iodide still reacting at that point? Yeah, it's still reacting. It's just, it's being formed just as much as it's reacting. So it's at equilibrium. Perfect. Then at equilibrium, what do we have? Everything. We have all of them. You will always have all of the species present at equilibrium. So at, oh, that's not how you spell equilibrium. At equilibrium, all species are present. Now, what I want to know, based on the graph, is this reaction products favored or reactants favored? Is it products favored or reactants favored? It's products favored, right? Here, HI is our product, right? So this is products favored. Hopefully that's pretty obvious to you that our products are way more massively favored than our reactants are, okay? So this is products favored, that's reactants favored. So what I want you to take 2 or 3 minutes, and I want you to answer the question here. What is the equilibrium position of the system? And what I mean by that is it products favored or reactants favored? I would like you, I'm not going to give you any more context other than that. The cup at the beginning is the initial state. The cup at the end is the equilibrium state. They give you the reaction down here, and they give you what X and Y look like. So you and a partner take 2 or 3 minutes to think about this, discuss it. If you want to count up some things, go ahead and count them up. It is a strawberry mango. Oh, strawberry bananas are pretty good. I like them.
Saw you licking the blade. That's dangerous. You cut your
Yeah, the blade only goes one way though. So as long as I lick the back side of the blade, we're good to go. It'll be fun.
Say that when you have snake tongues. I'll be looking like cornflakes.
Then I'll be a true Slytherin, won't I?
Yeah.
Oh, yeah, it does.
Yeah, but I'm also waves and see, when you're broke, you learn how to spend other people's money.
Okay, I'm going to give you 10 seconds to finish up your thoughts. Okay, is this system reactants favored or products favored at equilibrium?
I put reactant.
I'm hearing some people kind of murmur one of the words, but nobody's really telling me. Jaden?
React.
How do you know?
Because in the initial state, you have like a mix of both, and then once you get to equilibrium state, you have a lot more reactants than you do products.
So what I'm going to do is I'm going to circle the reactants in red, and then I'm going to circle the products in blue in each state. So let's take a look at the initial state, and a reactant I'm going to circle in red. So I'm looking for a single Y or two X's put together. So I see a single Y, two X's. I see a single Y. Nope, that's it. That's it. Woo, holy. So initially there's only two of those, which means all of these have to be products. 2, 4, 6, 8. Okay, so that's my initial condition. But we haven't established equilibrium yet. That literally doesn't mean anything at this point in time. Okay? So let's go back and let's circle a single Y or two X's put together. See, two X's, two X's, two X's, a single Y, and a single Y. 2, 4, 6. So at equilibrium, I see 6 of them, and hopefully that means there's 4 of these. Would you agree, at equilibrium, the reactants are favored over the products? Hallelujah. There you go. So we can say reactants are favored. Now what we're going to do right now is we're going to talk about one of the really big rocks of this unit. Definitions of what dynamic equilibrium are, that was kind of the first big rock we talked about. This is kind of the second big rock. I really want you to understand when I say that 9 times out of 10 on the diploma exam, there will be a question about what we're about to do, okay? So we really need to be paying attention. This is going to set up our understanding of the rest of the unit. So we're going to talk about ice tables. Ice tables, what the hell is an ice table? Well, an ice table tracks the change in an equilibrium system. Ice table stands for initial change, and then equilibrium. What it is it's going to be a table, and we're going to be accountants, and we're going to have to keep track of the change, either the gain or the loss of my reactants and my products. We're really going to focus on how can we get an equilibrium, and the way we're going to do that is we're going to use the initial plus or minus the change will give you an equilibrium. I'll give you an example. If my initially, if I had 0.80 moles per liter of something, And at equilibrium, we ended up with 0.30 moles per liter. I'm curious, do you know what my change was? If I started with 0.8 and I ended with 0.3, what's the difference between those? Yeah, so is it a positive or a negative change? It's a negative, and it's 0.50 moles per liter. Hopefully you can understand how these two together, those two together have to equal this. Does that make sense? That's how we're going to track our changes using an ICE table. Whatever our initial is, plus or minus our change, has to equal our equilibrium concentration. Some tips and tricks about this. If no information is given about a substance, you can assume the initial is 0 for the most part, okay? We'll talk about when then that's not really true. Remember that the initial plus or minus the change, that's exactly what we did there. The initial plus or minus the change is equal to the equilibrium, right? If you start with 5 and you lose 3, well, at equilibrium you must have 2. Okay. These tables can also be used to calculate chemical amounts. They're not just for moles per liter, they can also be just for moles. But whenever possible, I would like you to write this down. Whenever possible, change moles into moles per liter by dividing by the volume. Moles per liter is going to be way more useful to us in 90% of the cases, but in some cases it doesn't really matter, so whatever, it's all good. Let's go through an example. And we're going to set up ICE tables very specifically, like in a very specific way. So, in the following equilibrium, H2 plus I2 gas gives us, right, both ways, this is that double-headed arrow kind of, 2HI. This is the exact same equilibrium reaction that we've been talking about for a little while. The initial concentration of H2 is 1 mole per liter, and the equilibrium concentration of I2 is 0.25 moles per liter. Calculate the equilibrium concentration of HI. The way I want you to set this up, you've got a table, and you've got the words initial change equilibrium, or you can just use I, C, and E. Above the table, I want you to have a column for every single chemical in your reaction. How many chemicals are in this chemical reaction? I see 3, so you need 3 columns. The way I always do this is I put H2, I2, and then HI gas. I rewrite the entire equation above the ICE table. It's the best way to do this. Now let's go through here and let's try and identify any information that they give us in the problem. The initial concentration of H2 is 1 mole per liter. So you're going to see H2, and where it says initial, what number am I going to put? Yeah. I'll put 1.00, but you can put 1, right? It's the same thing. What's the only other piece of information that they're giving us?
Equilibrium concentration of I2.
So they're giving us the equilibrium concentration of I2 is 0.25 moles per liter. Now we're going to have to take in some of those assumptions that we looked at in the previous slide, okay? And I want to kind of amend one of them. If it says you have 1 of this, but it says you have none of this, or it's kind of implying that right now, that's not totally true. If you have none of this, can this reaction proceed at all? No, you can't, okay? So an assumption you kind of need to make is that because they have the same coefficient, well, they're saying, really what they're saying is 1 mole per liter of both of our reactants. That's really what they're saying. So 1 mole per liter of both of our reactants. Did they say anything about any of the HI being in the flask initially? Are there any products in here initially? No, there aren't. So we're going to assume that there are no products at all. I don't know about you, but we can complete one of these columns. One of these columns we can complete. Now let's think about this for a second. Are we going to be making products, or are we going to be making reactants? Are our reactants concentrations, are they going up or are they going down? They're going to be going down. Can you see, even if I didn't have this, can you see how the only thing that can happen is our reactant concentrations can go down? Does that make sense? So what I'm going to do above here is I'm going to say negative and negative. And if we're losing reactants, what do we have to make? Products. Now this is a really big leap for some people. This, what I'm about to say, is a really massive leap. For every 1 hydrogen, how many iodines react? 1. For every 1 hydrogen, how many HIs do we produce? 2. So the change is going to be proportional to the coefficients. If I lose 1x, I have to lose 1x here. Do you agree? For every 1 of these, I have to lose 1 of these as well. Now, for every 1 of these that get used up, how many of these are made? 2x. And we're going to use the placeholder of x because immediately we don't actually know how much changed, okay? Now I'll put that final puzzle piece back in here. You should always be looking for a column that you can finish. Can you finish anything for this first column? No, you can't. Can you finish anything for this column? Yeah, you totally can. What was the change if we went from 1 to 0.25? Negative 0.75. So negative 0.75. Well, this is really interesting. Our change was negative 0.75. So what that means is our x was 0.75. Does that make sense? We lost 1 something, and that something was 0.75. So how much of this did we have to lose as well? Negative 0.75. And this is the really big leap for some people. How much of this stuff did we gain?
150.
Yeah, whatever double this is, right? For every 1 of these, we gain 2 of these. So go 2 times that, so that's positive 1.50. So now we can find all of the equilibrium concentrations. What's the equilibrium concentration of hydrogen? Once we establish equilibrium, what's that concentration? 0.25. Once we establish equilibrium, what's the concentration of hydrogen iodide? 1.50. So we can answer our question. Calculate the equilibrium concentration of HI. What I would say is equilibrium concentration of HI gas is equal to 1.50 moles per liter. Was that okay? Was that fairly straightforward? Okay. We're going to go, yes, sir.
Would it, okay, I'm not exactly sure how balancing works in this circumstance, but it seems like it should be equilibrium 2HI gas is 1.5 moles per liter.
Yeah, but but all we're saying, I totally understand what you mean.
Oh,
like,
actually, I get it.
Yeah, okay.
Yeah, okay. Sorry.
Okay, so we're gonna do one more. We're gonna do one more example, and then I'm gonna ask you to do some questions for me. So let's do one more example, and let's set it up together. I'm gonna give you a crack at it. I'm gonna give you a kick at the can, and then we'll go through it together. So if the initial hydrogen amount concentration is 10, and the initial nitrogen concentration is 8, and the equilibrium concentration of ammonia is 1, calculate the equilibrium concentration of hydrogen, blah, 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 blah. You've got an ice table here already. Somebody tell me, how do you want to set up this ice table? Somebody illustrate to me how you want to set up this ice table. You guys are all hard at work, I'll just let you go.
ICE and the
Yeah, we're gonna put ICE, and then I'm gonna write my reaction above these columns. Everything should, it doesn't have to be, but whenever possible, everything should be measured in moles per liter. So we know we're starting off with 10 of the hydrogen. We're starting off with 8 of the nitrogen. And the equilibrium concentration is 1.00. Give you a couple minutes to work on this. Yes. Any questions? I'm not seeing everybody put plus 1x or minus something x or plus whatever x. Not seeing everybody put that above their reaction. That might help you. The reciprocal is not the opposite. It's hard to say opposite, right? So you say have a fraction, so you flip your denominator and you back to position. So if you have a 1 over 2, okay, so 5. What's the reciprocal of 5? How do you write 5 in the caption? 5 over. Good. Is that okay? What's the reciprocal of 290? 1 over 290. Canada and up, but maybe it's the same thing. Okay. Yes. Yeah. Okay, so initially, did they say anything else, like about how much of your products are in there? No, so you just assume it's zero. Yeah. Yeah. If one of these reacts, how many of these does it have to react? 3, so 1x and 3x. And how many will be made? 2x. Now you need to think, are we going to gain or lose? Okay, so do you start off with any of this? So can you lose any of that? If you have nothing to begin with, can you lose any of that? No. What's the only option? Gain. So you got to put plus there. If you're gaining products, what do you do to your reactants? Is that okay? Okay. Ooh, do it. Okay, so we're gonna do this whole thing together. And regardless, if you, it doesn't matter how confident you are in the answer that you got. It doesn't matter how much you struggled when you went through this example. I just want you to pay attention up at the front, and I want you to really focus on how am I helping myself set up this problem, right? Don't jump straight to the answer, because if you jump straight to the answer, you're never going to get anywhere. It's the process that's going to help us. So this is all the information that we're given in the problem. Everything in blue, that's all just the information that we've been given. We've given the reaction, we're given the initial concentrations of those two things, and the equilibrium concentration of that. The first thing I want to think about, first thing I would think about, is which way is this reaction going to go for the most part? Is it going to go in the forwards direction mostly, or in the reverse direction mostly? Yeah. Did it say we had any of our products initially? We have to assume that there's 0 of that initially. That's our first main assumption that we have to make. Well, if we have none of this, can we lose any of this? No, we have to gain this. We have to be making this. So I would say plus, minus, minus. Does that make sense? If you're gaining products, you need to be losing all of your reactants. Not all of them, but everything on your reactant side has to have a negative beside it. So now let's use our coefficients to figure out how much are we going to gain and how much are we going to lose. We don't know that right now, but we can use it to help us. So for every one of these that reacts, how many of these are going to react? 3. So if I lose 1x, I'm going to lose 3 x's. Right? If I lose 1x here, how many do I gain here? 2 x's. That's really going to help us. Now that we have everything set up, now we can start solving the problem. Only now can we actually start solving this problem. Is there a column that you can complete? Yeah, absolutely. So what I want you to think about is, obviously we must be gaining 1x here. Would you agree? We're gaining 1 mole per liter. But that 1 mole per liter, how many x's are in that 1 mole per liter? 2. So what is your x equal to? 0.5. Another way of thinking about this goes back to the hint that we were talking about. This is an equation here. This plus this equals that, okay? But if you don't know, 0 plus 2x equals 1 mole per liter. That's the equation I can get out of this. 0 plus 2x, which is our change, right? We must be gaining 2x here. That's equal to 1. Well, if you rearrange this, right, that doesn't matter, divide by 2, our change must be 0.5. And hopefully that makes sense. Yep, our change is 0.5, and we're gaining 2 of them, so that's 1. Hopefully that makes sense. Here, how much are we losing? How many x's? 3. So what's 3 times 0.5? So negative 1.5. And if we're losing 1x, so we're losing 0.5, and then now we can complete this. 8 minus 0.5, 7.5 moles per liter. 10 minus 1.5 is 8.5 moles per liter, and we've got 1. So what it's asking, calculate the equilibrium amount concentration of hydrogen. Okay. Concentration of hydrogen at equilibrium is 8.5 moles per liter. That's the idea behind that. Now, for some people, that's really tough, and I would never judge you for that. This is a very kind of interesting, it's a combination of chemistry and mathematics, and it's pretty tough at the beginning. I'm going to give you 3 problems that I want you to work on. And once you finish these problems, there are some ice table questions in your major assignments that you could start working on if you really wanted to. Sorry, your question was, can you get caught up on the notes? Yeah, if you want to take your cell phone and pop up to the board here, you can take pictures of the notes. I don't have the notes on the Google Classroom. I never put up the notes until we're done this entire notebook file, and then I'll put them up on Google Classroom. Take a picture of somebody else's notes. Yeah, or you can take a picture of these notes, whatever you want. Okay. In these questions, you have to do lots of things. There's a lot of problems here, okay? Can you perform this ice table question without a balanced chemical reaction? No, you need the balanced chemical reaction to figure out if you're gaining 1 or losing 5 or whatever, okay? So that's what you should focus on first. You should focus on writing a balanced chemical reaction first. Let me know if you have any problems. I'm going to be wandering around trying to help people.